Solving inequalities. A polynomial inequality takes on the form f of x is greater than 0, f of x is greater than or equal to 0, f of x is less than 0, f of x is less than or equal to 0, or even f of x does not equal 0. Inequality, to not be equal to. It might have the or equal to parts, but an inequality means to not be equal to something. Okay, now this we don't really see too often, so don't worry too much about it. But technically, it is an inequality. To solve something like f of x is greater than 0, you can think of that as trying to find all the x values that make f of x positive. Okay, graphically speaking, this would be all the parts that are above the x-axis. Okay, all the x's, though, would be the solutions that would cause the graph to be over the x-axis. Then you've got the opposite. F of x is less than 0. For that, you're looking for all the x's that make f of x negative. You're looking for all the x's that would make the graph show up underneath the x-axis. For example 1, we're given the function f of x is equal to x plus 3 times x squared plus 1 times x minus 4 to the second power. What we're going to start with is determining any real numbers of x such that f of x is 0. Okay? We're going to determine when this is equal to 0. Okay, now we got it in factored form, which is going to help. So you do have a real value at -3. If you were to put -3 here, the whole thing becomes 0. You also have a real value here using 4. And technically, that would be a double root or double 0 because it's raised to the second power. The middle factor that we have here, x squared plus 1, that does not actually produce any real numbers that would cause it to be 0. If you take a look at x squared, no matter what you put in there, it becomes positive, which means that if you have a positive number plus 1, you can't get 0. Okay, that factor does not produce any real zeros. Okay, so now what I have here is just a horizontal line. What I'm going to do is mark off the zeros that we've got. We got -3, we got 4. And none of this needs to be evenly spaced. This does not have to be a number line where things are evenly spaced. We just need to make sure that they're in the right order. Okay, now what we're going to do is take test values. We're going to think of sample numbers of x that fit within these little intervals that are separated by those zeros. We're going to take test values. We're going to plug them into the function to see if we get back a positive or a negative. Okay, for example, between the two of these is 0. If we were to plug a 0 into each of those, what would we get back? More importantly, though, do we get back something positive or do we get back something negative? Okay, so as we do this, when you plug in the 0, just be thinking positive and negative. If we put a 0 here, we get +3. You're going to get a positive. No matter what you put here, even 0, you're going to get a positive. What you put here, no matter what, is going to be positive. You might think that's weird for just a second, because if you put a 0 here, you get -4. However, it's going to get squared, which is going to give you a positive. So the graph between -3 and 4 is going to be on the positive side, because we get all positives here. Okay, let's take another value, something that's over here. Let's take 5. Okay, we'll just take 5. When you plug 5 in here, you're going to get an 8, which is a positive. Plug a 5 here, definitely positive. Plug it here, definitely positive because it's squared. Okay, so we got all positive here. The graph exists above here. The graph also exists above here, which should make sense because at 4, you've got a double root. It's going to bounce against that spot, which should make sense because at 4, you're going to have a double root or double 0. It's going to bounce in that direction. Okay, over here, let's think about maybe -4 if you were to plug that in. Okay, if -4 goes in here, you get back -1, so you do have a negative. The other two, as discussed before, they have to be positive. You don't really even need to pay attention to them. Okay, so the graph is going to be underneath here. It's going to be positive here, positive here. Plus, we've got that double root, that'd be there. Okay, so we'll be coming from the bottom, crossing through here, going up, bouncing in that spot, definitely coming up. All right, so here's a picture of the actual graph that we've got. It does approach from the bottom, makes contact at -3. It goes up. There's an extra bend here in the middle. It does come back down at 4, bounce off, and then head upward. Okay, so as a quintic function, degree 5 function, it actually has 4 bends in it. You've got a bend here, you've got a bend, you've got a bend, you've got a bend there. So you actually get 4 of them. All right, so consider all of these problems you could have been asked to find solutions to. Okay, when is this function greater than 0? When is it positive? That'll be from -3 to 4, then 4, so on. We actually have to refer to a little bit of a break here because we're strictly looking at when it's greater than 0. And at 4, it is technically 0. So that's going to be open as well. This will be open as well. So we're going to get open at -3 up to 4, then 4 to infinity. However, if we write this as greater than or equal to 0, we get to include the 3. We also get to include the 4, which means you don't need 2 intervals. You get bracket -3 to infinity. All right, for less than 0, that would just be this part here. So we would have -infinity to -3, which will be open. Less than or equal to 0, you are going to have -infinity to -3 included, and you're going to pick up a single point right here at 4, which you just have to state that way. It starts at 4, it finishes at 4. It's the same number, but that includes that single location. All right, let's solve this quadratic inequality. What we have is x squared minus 6x minus 30 is less than -3. What we're going to start with is moving that -3 over to get a 0. So we're going to get x squared minus 6x plus, actually that'll still be minus, minus 27 is less than 0. Okay, now that everything's been isolated, we're going to start thinking about factoring. Okay, what multiplies to give us -27, but adds to give us -6? That would be a -9 and a +3. So our roots are going to be at 9 and -3. All right, so on my line, I'm going to mark that off. We got -3 and we got 9. In between those, we should keep that there. In between those, we do have a 0, so that'll be my first test value. Okay, and if I were to plug a 0 in, I would get -9 and a 3, which would give me negative. So we're going to be on the bottom side here. Okay, being that it's a quadratic, you should be able to expect the rest, but let's just go ahead and consider what would happen. If we plugged in 10, you would get 1 times 13, positive and positive, so you'd be up here. If you plugged in -4, you'd get -13, you would get -1. The negatives would cancel to get positive. Okay, so the graph is going to be up here. It's going to dip, hit that spot, dip lower, come back through at 9. So to answer the question, when is this less than 0? That is here. It's going to be an open interval, -3 to 9. Example 3, suppose that we want to solve this greater than 0 analytically. That means no graphing. The rational root theorem can be applied to find rational roots. If one does exist and is found, any remaining roots could be easily found using factoring or the quadratic formula. All right, to start things off, these would be all the possible rational roots that we could get from this. We have a lot of them. So for the sake of just expediting this, I'm going to give you one of the roots. One of those roots will be 4. Okay, now this is a cubic. This is a cubic, so we expect that there could be 3 roots. So that would be one of them. That would also mean that x minus 4 is one of the factors. Okay, so what we're going to do is use synthetic division to divide that out. Okay, we're going to set up our box. We're going to put in a 4 because the 4 is the actual root. The coefficients All right, and let's go through synthetic division. We'll drop this 2. 2 times 4 gives us 8. We get 1. 1 times 4 is 4. We get -6. -6 times 4 is -24, which gives us 0. So, in fact, this is a root. Okay, it comes back as a 0, which means that we have a root. The remaining part here is going to represent 2x squared plus x minus 6. And for this, I'm going to factor by parts. 2 times -6 is -12. All right, so we'll split the middle term into a positive 4x and -3x. Okay, that way they add together to give us a positive 1, but their product would give us a -12. We're going to drop these down. Technically factor by parts now. From the first two terms, we can take out a 2x, which leaves us with x plus 2. The second set needs to do the same thing. We can factor out of that -3. So overall, the factors that we have for this whole thing, we've got this, we've got x plus 2, and we're going to get 2x minus 3, which tells us that our roots are going to be at 4, -2, and a positive 3/2. All right, now to solve the inequality, to figure out when this is greater than 0, we're going to run test values. Okay, so I got my line ready. The values I'm going to mark off are going to be -2. We're going to have 3/2, which is the same thing as 1.5. And we're going to have a 4. Okay, now this is a cubic. This is a cubic, so we expect that it's going to go up, back around, and through, or it's going to come from the top, go through here, and then just wave through that way. So honestly, we just need to do one test value. Usually, the easiest test value is going to be 0. So 0 is located here, okay? So if I plug in a 0, I'm going to get a negative times a positive times a negative. The negatives will become positive. The positive, of course, is positive, so overall, the graph is going to be positive here. Okay, now just to test it out a little bit further, we could check other values. Suppose we plugged in a 2, which would be here. If we plug that in, you'd get 2 minus 4, which is a negative. You'd get 2 plus 2, which is a positive. Over here, you would get 4 minus 3, which is a positive. So overall, that would become negative. So the graph is down here. Okay, so it appears the graph would be going through here, coming back around, and through that direction. So to answer the question, when is this greater than 0? That'll be here and on that far end. So we have two parts. Okay, strictly greater than 0, open interval at -2, up to 3/2, and anything greater than 4. All right, and last what I'm going to do is take a look at a couple unique cases. The first is going to represent a case when the polynomial, if graphed, does not make contact with the x-axis. Okay, so this is a graph of y equals x squared plus 5x plus 8. You're going to notice that it does not make contact with the x-axis. So if you ask these questions, when is it less than 0? The answer to that is never. This is what we call an empty set, which you can write like this. That would be an empty set. There are no values where this is negative. However, when is it greater than 0? That would be for every possible x. All right, now the tough thing about this is that sometimes you just have to graph them. If you attempt to do this analytically, that means that if you're looking for factors and intercepts, you might run into a wall. So sometimes you just actually have to graph it. Okay, the other case is going to represent when the polynomial bounces up against the x-axis, where it just makes contact, then turns around the other direction. We would also call that being tangent. Okay, now in this case, when is this strictly greater than 0? Not for every number. It would not be greater than 0 at that point of tangency. So we'd actually have to write as two intervals. You get negative infinity up to 5, then 5 to infinity. It just skips over that one point. Okay, when is it less than or equal to 0? Well, it's never less than 0, but it is equal to 0 at 5.
Later, blah.